Yep.
Okay, you're recording. Hi everyone, welcome to Recitation 12, and tonight we're gonna talk about sampling. Let's see what we have in our slide today.
Alpha, your screen's not
Uh,
shared.
yeah, wait, what happened? It said host disable screen sharing. Can you allow me, please?
Oh.
How are you everyone? Did you have fun during the break?
Yeah.
Okay, I think I can now share. Not a lot of break or not a lot of fun.
Both. Not much break, not much fun.
Both. Who are you? It's life, right? Yeah, we're gonna get through this together. I tried sleeping 72 hours. It didn't help me too. Okay, sampling theorem. So today we're gonna cover sampling theorem and there are some tips that we can use to solve the sampling theorem question. So we need to find, usually it will give us time signal and like this, and we need to change it to frequency signal. Can you see my screen?
Yep,
Yeah.
you're all good, Alpha.
Cool, okay. And after that, we're gonna identify omega m, which is the Nyquist frequency. That is gonna make the frequency signal here equal 0 in the duration in the period of maximum Nyquist frequency. And to make it in picture form, I am gonna share this graph. I made this at my note a while ago when I take this class. So Nyquist frequency, we can also call it bandwidth too. So if we have like, assuming we have this time signal xt, which have the frequency, okay, if we change it to frequency domain, the frequency with 50 hertz, and we have the signal yt, and corresponding frequency is 100 hertz. So, and I'm gonna done some operation to these time signal, and usually the question will ask me to find the bandwidth or Nyquist frequency or Nyquist rate, which is gonna be something in frequency domain. And let's see the first case. If we add the time signal together, and I want to know what would be the bandwidth that I want to choose. And let's see this graph. It's gonna be when I add the time signal together, you can see that we will choose the figure 1, so that when we choose our sampling our signal, we'll get all of the, it will cover all the period that we have. And the same as for subtracting time signal. When we subtract the time signal, it will look like something like this, but still we want to cover from negative 100 to 100. Therefore, we want to cover the bigger frequency so that we don't lose anything. And case number 2 is convolution of time signal, and which is gonna be the product in frequency domain. If you look at the property of Fourier transform, right? When we have time signal, multiplication of time signal, when we change it in, okay, not this table, but gonna be some other table. If we have convolution of time signal and when we change it in the frequency domain, they're gonna be multiplying together. And our graph will look like something like this. So the bandwidth that we want to choose would be the smaller one. And Another case, product of time signal, and it will be the convolution in frequency. So if we perform convolution of smaller signal of 50 Hertz with 100 Hertz, the bandwidth will be the addition of the two time signal. So addition of the two frequency. In this case, 50 plus 100 is 150 Hertz. Okay, before I begin our problem solving, do you have any question on this part? Any TA would like to add something? Can you hear me well, everyone?
Yes, it's all good.
Yep.
Go
Yeah, no
ahead.
question.
Thank
we're
you
good.
so much. Okay. Thank you. Okay, let's start with our first problem. So our first problem is gonna be this one. You still see my screen? It should be number one instead. Okay, we have time signal xt and yt and the corresponding Nyquist rate. It is still in time. So will be omega naught and 2 omega naught respectively. And the question asks us to find the Nyquist rate of these two operations. Do you have something in the chat? Oh, thank you, Jade. Okay. All right. So if we talk about Nyquist rate, it is 2 times of Nyquist frequency. I think you guys have probably learned this in class already, right? But if we have a signal, we want to sampling it like 2 more times larger than the signal so that we won't lose the signal. And this is one point that I want us to remember. And also another point to remember is that sometimes we call a Nyquist frequency interchangeably with bandwidth and sometimes maximum frequency or omega m in this case. Okay, and from this information that we know, and we know that the corresponding frequency of time signal xt and yt are omega naught and 2 omega naught respectively. Can anyone help me from the given Nyquist rate? Can you help me find the Nyquist frequency, please? Anyone would like to try this? You can shout out or
I mean, is it
type
just
in
omega
chat.
not over 2? And then the second one's just omega?
Yes, it is. Thank you so much. Okay, so we said that the Nyquist rate is 2 times the Nyquist frequency. Therefore, Nyquist frequency will be Nyquist rate over 2, right? So for xt, the corresponding Nyquist frequency will be omega naught over 2. And for yt will be omega naught. Cool. And if we know this, now we can solve the problem. Let's start with A. We have this time signal ct equal xt plus xt multiplied with yt. And it asks us for Nyquist rate. But the first step that we always want to do is to find this signal in terms of frequency. We want to know frequency domain. Can anyone tell me if I have a time signal and I want to change it to frequency domain, what is the operation that I have to do? Start with if. End with transform. Anyone would like to shout out?
Just Fourier transform, right?
Yes, Fourier transform, thank you. Therefore, what I'm gonna do is to apply Fourier transform to both sides of this equation. Let's try it, shall we? So on the left-hand side, I'm gonna get the signal xj omega, and this is gonna be, we're gonna need the Fourier transform property to do this. Okay, I have et whole xt plus 4t times yt. Okay, I change it to frequency domain. X is gonna change to frequency domain, but now I have xt times yt, right? And that is the multiplication of time signal. When we change it to Fourier transform, what I will have is 1 over 2 pi times xj omega and yj omega. Anyone have a question on this? Are you clear on this? Wait, I'm not sure I'm using the right one. I
Yeah,
should
they
look
need
at
to be
this.
convolved.
Oh, thank you. Yeah, and convolve. You know, I'm just gonna write it down here. I don't think I pull out the right table. I'm gonna fix that later. Okay, but thank you for the note. It's gonna be for this part, gonna be 1 over 2 pi times xj omega convolved with yj omega. Cool. Okay, anyone have questions about this part? Okay, I assume no. So, and now we have two frequency signal, not actually two. Okay, let's say I'm gonna call this chunk. I'm gonna make it a new signal. I'm gonna call it x1 j omega. Okay. And can anyone remember what is the Nyquist frequency of xj omega?
Omega naught over 2.
Yes, omega naught over 2, Nyquist frequency. I just write NF is omega naught over 2, right? And this x1j omega, what would be the Nyquist frequency of this? We know that this thing stems from the
It's the
multiplication in
sum.
time signal.
So 3 omega naught
Yeah.
over 2.
Let's see. It's the convolution, right, of the two, of the frequency signal. Therefore, yes, you're right. It's the summation of the two. Therefore, our Nyquist frequency would be omega naught over 2 from xj omega plus omega naught, which equal 3 omega naught over 2. And that's it. But I got a question for you now, everyone. Do you know why I don't do anything to 1 over 2 pi? Why is that so? Like, is this significant at all? Like, why
It's
don't I
just
apply to it?
it's an amplitude scale, right? Scalar.
Yes, it is. It's just gonna be scaling factor, and it only affect the amplitude of the spectrum, frequency spectrum, but it doesn't affect the frequency of signal itself. Therefore, we're gonna neglect that scaling factor or 1 over 2 pi. Okay, great job, everyone. Now we know each Nyquist frequency of each part now. But okay, it's not just that part, right? Because now it's doing addition. So what about addition of the signal? What would the Nyquist frequency or bandwidth be? Let's go back to this
The
one.
largest.
Okay, if I adding them together, time and frequency, yes, the bandwidth is gonna be the bigger one. And between these two, what is the bigger bandwidth?
3 pi, or sorry, 3 pi, 3 omega over 2.
Yes, it is. Thank you. So therefore, we know that Nyquist frequency of Vj omega is V omega naught over 2. Or I can write it in this way. I'm gonna add more detail in the note that we will post later. We can say that x j omega equals 0 for omega more than 3 omega naught over 2. They have the same meaning anyway. Okay. Now, we know the Nyquist frequency now, right? But the question, what the question asks us? The question asks us for the Nyquist rate. Therefore, you remember this equation, Nyquist rate is 2 times Nyquist frequency. And we need to find Nyquist rate. Okay. From this equation, can you help me find the Nyquist rate for this question, please?
It's 3 omega. Or sorry, 3.
Yes, just
Yeah.
3 omega naught. Yes, you're right. It's gonna be 2 multiply 3 omega naught over 2. And that is 3 omega naught. And that is the Nyquist rate for this question. Boom. Great job. I give you a thumbs up. Does it look like a thumb?
Sure.
Okay. Okay, cool. Now, impressive for this question. Anyone have question on this one?
Why is the convolution equation like 1 over 2 pi and not just like when you're going between time domain, the convolution to frequency domain, it's just like convolution to multiplication. But when you're going from time domain multiplication to frequency domain, it's like the 1 over 2 pi is just like the period or what?
Yeah, let me check the table. I'm not sure if I'm using the right table to show you.
Yeah, that should be right. Could you repeat your question one more time? Sorry.
I'm just curious, like it's not really like a constant question, I guess, but I'm just curious like why it's
Like,
like
what's the purpose of the
when you start
significance of
with
that 1 over 2 pi scaling factor?
yeah, when you start with convolution, you can just straight go to like multiplication, but when you like start with multiplication, you have to like use like the 1 over 2 pi. Is that like the period of the frequency or is it just because?
That is a great question. I think
Yeah.
what is the sorry, give me one sec here. I am not positive where that comes from, to be honest.
Okay, no worries. I was just curious.
Sorry.
You know what? Let me check the table and I will get back to you because I'm trying to find the Fourier transform property table. I'm not sure if it's only this one or there is more. So I'll get back to you on that. But yeah. Okay. Apart from that, is there any question?
I wonder if it has to do with the fact like that omega equals to 2 pi f, maybe? I'm not entirely sure.
Omega.
Omega equals 2
Oh,
pi f.
you mean the 2 pi in this part?
Yeah. I'm
Oh, and
not,
it goes from
The
time,
1
and
over
then
2
f is
pi?
1 over t, so that's why it's 1 over 2 pi.
yeah, like f is in like hertz, right? 1 over seconds, but omega's
Yeah.
in like radians. I mean, regardless though, it's just a scaling factor, and like if you remember from today's lecture, the scaling factor doesn't affect like the bandwidth and all that. So, and the frequencies and not. I'm not too sure about the 1 over 2 pi. I mean, it kind of shakes. I mean, it's because of the math, but I don't have a great like intuition explanation for it.
Yeah. I honestly got this from the solution made by a professor, but so I'm gonna verify that and get back to everyone. But yeah, the main point is that if we have multiplication in time domain, when we change that into frequency domain, it's gonna be convolution. And the bandwidth of convolution of the frequency signal is gonna be them adding together. This part, let me check about it and get back on that. Okay, next question. We have this signal. Okay, can anyone remember the first step that we should do? Yes, it is Fourier transform. Apply Fourier transform both sides. And I'll get V J omega equal A X J omega minus J omega and Y J omega. Okay. I wanna check with the table, but I'm not sure if I have the right table here. Okay, I actually have the right table, I think. Yeah.
Yeah, I think your table's good.
For okay, that's cool then. For um okay. For this part, it is gonna be just linearity, right? So you still have A X J omega. That right? And the later part is differentiation in time. And we're gonna get J omega X J omega. Cool? Is that clear? Okay, okay. I get that's clear. All right. Let's look at the first part. we want to know what is the Nyquist frequency of this one. Anyone would like to give it a try? We know that A is just a scaling factor, right? And it doesn't affect frequency. Therefore, the Nyquist frequency of xj omega should be omega naught over 2. Is that cool? Is that clear to everyone? Okay, I guess that is clear. And for the first part is gonna be that. Now let's look at the second part. We have something in frequency multiplying with y j omega, which is also in frequency. And this part is gonna be a little bit tricky. For this part, you know that y j omega exists between, okay, this is my abbreviation of between negative omega naught and omega naught. Why is that so? Remember the Nyquist frequency is omega naught. Basically, it just means that the Nyquist frequency of y j omega is omega naught. Yeah, remember this one? Y j omega equals 0 for absolute omega more than omega naught. Similar thing. But we also have j omega 2 and j omega exists for all the omega. Why is that so? Because omega can be anything. It can be anything from negative infinity to infinity, right? So if we say the bandwidth, we can say that the bandwidth of j omega or Nyquist frequency of j omega is actually infinity. Okay, are we clear on this? Anyone have question on this part?
Wouldn't it be? So if you're multiplying something that doesn't exist when it's greater than omega naught, wouldn't the bandwidth just be omega naught plus minus omega naught, right?
Yes, that's another step. Yeah, thank you for solving that. Because we have yj omega multiplying with j omega.
Oh, you're saying
Therefore,
that NF for just JW is infinity. My bad. Okay.
yeah.
I thought you were saying the
Oh,
whole
I
thing.
thought you're helping me solve the next steps.
Oh, no. Okay, no. Okay.
Okay,
Yeah,
but
ignore me.
yeah, but I think we're in the right direction. They're multiplying together, right? Therefore, if we have the multiplication of the frequency, we're gonna choose the smaller bandwidth. So what is the smaller bandwidth? In this case, this one or this one? Is it gonna be between negative omega naught and omega naught, or between negative infinity to infinity.
Omega naught.
Yes, thank you. So the Nyquist frequency of this term would be omega naught. Cool. And now we have to frequency domain signal subtracting together. Can anyone tell me what would be the Nyquist frequency of Cj omega? What is it? They're subtracting, right? We have the subtraction. It should be, what should it be?
Big one.
It should be the bigger one. And what is the bigger one?
Omega naught.
Yes, it's just gonna be omega naught. Thank you. And now we know what is the Nyquist frequency. We need to find the Nyquist rate. And can you remember what's the Nyquist rate? In
Just
terms of
2 times that.
Nyquist frequency? Yes,
Times it
it
by 2.
is. Correct. Therefore, just gonna copy this again. Our Nyquist rate for this question would be 2 times Nyquist frequency, but it's not omega 3 omega over 2. No, okay, it is omega. Not. Therefore, our Nyquist rate would be 2 omega naught. Great job. Okay. Anyone have question on this step? Okay, if you don't, let's move on to the next question. That is our problem 1. Now let's look at problem 2. We have the signal xt with Fourier transform xj omega undergoes impulse train sampling to generate, okay, this signal, this long term, where we have t period is 10 to the power of negative 5x, and given that xj omega not equals 0 for absolute omega not more than 15,000 pi, can xt be recovered from the signal xpt? Okay, let's try to see if this, oh, spoiler alert, sorry, okay. Let's try to see if this signal can be recovered from xpt. Okay, given what we have from the question, can anyone tell me what would be the Nyquist frequency in this case?
Just 30,000. I can't really see it.
Pardon?
Oh, sorry, 15,000.
Yes,
Yeah, or no?
15,000. Thank you. It is correct. Yeah, from this part, right? If xj omega equals 0 for absolute omega more than 15,000 pi, that means that the Nyquist frequency of xj omega is 15,000 pi. And that's what we know. The next step that we want to do, so for a signal to be recovered completely from sample signal, we should have the sampling frequency that is greater than 2 times maximum Nyquist frequency. What does it mean? What do I mean by that? It means that sampling frequency this is sampling frequency, has to be more than 2 times of maximum Nyquist frequency. This is our Nyquist frequency. Maximum Nyquist frequency. Okay. Therefore, we want to find omega A sampling frequency. We want to find this so that we can compare it to maximum Nyquist frequency. If the sampling frequency is more than 2 times of the maximum Nyquist frequency, that means the signal is recoverable. Otherwise, the signal is unrecoverable. Cool. But the question doesn't give us sampling frequency at all. So how will I do that? Do you remember something in physics when we have omega equal to pi f, where f is frequency, which is gonna be 1 over t, which is period. Therefore, we have omega equal to pi over t. And in this case, we want to find sampling frequency, sampling omega. Therefore, we can find it now. Because why? Because we were given the t. And because we were given t in the question, we can find out what is the sampling frequency in this case. All right. So from the condition of the signal to be recovered, I want to have my omega s more than 2 omega n. And from this line, we know that omega s is 2 pi over ts, right? Which I wanted to be more than 2 omega n. And let's see, I'm gonna divide the two sides by 2. And I'm gonna switch the side. Therefore, I have T s should be less than I over omega, maximum Nyquist frequency. Is this one clear? Okay. I assume that everyone can catch me up in this part. Therefore, we want to prove if this is true or not. If this is true, that means it's recoverable. But if it's not, that means not recoverable. So we were given t equal 10 to the power of negative 5 seconds, right? 10 to the power of negative 5 in a second. which is less than, I assume that this is less than pi over omega naught. What is our omega naught? Not omega naught, I'm sorry, omega m, our maximum Nyquist frequency, which we already determined from the question that our omega m is 15,000 pi, right? So this is gonna be pi over 15,000 pi. Cut. And I wanna check if this is true or not. If 10 to the power of negative 5 is less than 15,000. Okay. And we find that from calculation, 1 over 15,000 is 0.66 times 10 to the negative 4 seconds. Is this part less or more than the given period, the given t? Anyone would like to try answering this? Is this more or less than that?
It's more.
It is more, yes. Therefore, t, let's start. 10 to the power of negative 5 is less than 0.66 times 10 to the negative 4 is 0. And t, sampling, is less than pi over omega n, and that will turn back, and that means that okay, it means that signal is recoverable. XBT. Cool. And that's it. We bring into this conclusion that the signal can be recovered. Okay. Anyone have question on this problem?
Oh,
Okay, cool. If you don't have question on this, I will pass it to another person. Next TA. Thank you so much, everyone.
All right, everybody. Let's go ahead and jump into question 3. So for question 3, we want to consider a signal x of t, which undergoes impulse train sampling to generate xp of t. Right? And our x of t is given, and then there's kind of a block diagram to understand the impulse train sampling, then getting out the sampled or the filtered function, right? So now if the signal was sampled at a sampling frequency of 75 pi, we want to determine if aliasing occurs. And then for part B, if we have a sampling frequency of 250 pi, we want to determine the range of values for cutoff frequency of a low pass filter that would ensure x of t is recovered from xp of t. So the first thing we need to do to solve question A we know that our sampling rate needs to be greater than 2 times our maximum rate. In this particular case, our sampling rate is given to us at 75 pi. So we need to determine what is our maximum frequency, right? So how do we go about that? Well, we're given that x of t is equal to sine 50 pi t over pi t squared. And we can use our Fourier transform to calculate what our maximum frequency from this function is going to be. So this looks like a scary Fourier transform, but with a little bit of algebra, we can make it pretty simple. So we're going to let x1 of t be equal to the inside of our square. So we're going to let x1 of t equal to sine 50 pi of t divided by pi t. And if we do that, we're able to define x of t as x1 of t times x1 of t. Now this makes it a lot simpler because we have essentially gotten rid of the square and just rewritten it in a new form. So we can take the Fourier transform of this, and that gives us x of j omega is equal to 1 over 2 pi times our x1 of j omega convolved with x1 of j omega. So from here, we need to figure out what x1 of j omega is equal to. And if we look at our properties table, so from our properties table, given a signal sine of wt over pi t, we get a transform of 1 for values of omega less than our w value, and 0 for values of omega greater than our w value. So if we take our x1, which was sine of 50 pi t over pi t, we know that our 50 pi is going to be our w term. Actually, I'm going to make this, it's kind of confusing because I got w's and omegas in here. Let's make this, someone give me a variable that's not used for a bunch of other stuff.
A.
Okay, we're making it a.
Oh my God, like my mind blanked. I think of letters.
I know, it's sometimes hard to think of variables because everything is already defined as something else. All right.
Yeah, easy. A for alpha.
Yeah, there
I
we
knew
go.
there was a bias there.
Okay, so we have our x1 of t, and we've identified, in this case, our a value. So we know that our x1 of j omega is going to be equal to 1 for values of omega that are less than a, and 0 for values of omega that are greater than a, which means we're going to have 1 for values of omega less than 50 pi, and 0 for values of omega greater than 50 pi. So if we remember, our maximum frequency is going to be the frequency at which our transfer or our function x of j omega becomes 0 past that frequency, right? So we have that defined right here, where at values of omega greater than 50 pi, our function is always going to be 0. So we know that for x1 of j omega, our maximum frequency is going to be equal to 50 pi. All right. So now we know our maximum frequency for x1 of j omega, but we need to find it for x of j omega. And we have that defined up here. So we're going to consider our x of j omega is equal to 1 over 2 pi x1 of j omega convolved with x1 of j omega. So we have our 1 over 2 pi we can ignore. And then we have x1 of j omega convolved with x1 of j omega. And we know that when we convolve two frequency functions, their bandwidths are going to add. So we're going to take our maximum frequency is equal to 50 pi. And then because it is x1 of j omega convolved with x1 of j omega, our other frequency is also going to be 50 pi. And we're going to add these together. So for our x of j omega, our Nyquist frequency, or maximum frequency, is going to be equal to 100 pi. So we've solved for our maximum frequency of our function x of t. Now we need to compare our sampling frequency to our Nyquist frequency. So we know omega s is equal to 75 pi. And to prevent aliasing, omega s must be greater than 2 times our maximum frequency, which in this case, we're going to have 75 is greater than 2 times 100 pi. Which right off the bat, we should say, okay, that's not correct. Oh, sorry, this should be 75 pi. Still not correct, right? So this is not true. So this is going to have aliasing. So we can say sampling theorem, which is omega s is greater than 2 omega m, is not satisfied. Therefore, we will have aliasing. So we've answered question 1, and we've determined that based on our Nyquist frequency of our function x of t, which we determined to be 100 pi, and our sampling frequency given as 75 pi, we do not meet the necessary relationship to prevent aliasing. So aliasing will occur, right? Any questions on that? I hope this all makes sense? All right, I'm going to take that as a no. Jump in with any questions if you have them. So now we want to solve part B. So we're given a sampling frequency of 250 pi, and we want to determine the range of cutoff frequency values for a low-pass filter that would ensure the recovery of x of t. So I think the easiest way to approach this is to visualize it. So we're given a sampling frequency of 250 pi, and we know from the question that we are doing impulse train sampling. So we know that our impulse train is going to look, well, it was terrible. All right, we're going for the built-in straight line. Hopefully this will be better. Oh, it would help if I could not hit the screen early. All right, good enough. So we know that our impulse train is going to be a series of impulse functions at our sampling frequency. Right? This is going to go both positive and negative. And then we know that our x of t, sorry, this should be not t, it should be j omega. Our x of j omega is going to have a frequency range. My hands are too shaky. From negative 100 pi to 100 pi, right? And that's just based off of our maximum frequency that we calculated above. So now, when we do this sampling, we're going to be multiplying them together, right? So we're going to get our xp of j omega is going to look something like this. Where we're going to have copies of our x of j omega that are spaced out at our sampling frequency. And to find the bounds of these functions, we can do our sampling frequency minus our maximum frequency, or for the other side, our sampling frequency plus our maximum frequency. And if this was, let's say, at the second point, we would have 2 omega s minus omega m, and 2 omega s plus omega m. And this would keep going on and on, right? But we need to determine where we need a low pass filter to recover our signal. So we want to recover this section, right? So we need our we need our cutoff frequency to contain our signal, but not overlap with any copies of the signal. So really, we're looking at this region here. right? Where we need our cutoff frequency to fall somewhere in between those two lines. So we can write that out as 100 pi is going to be less than our cutoff frequency. But our cutoff frequency needs to be less than our sampling frequency minus our maximum frequency. So we're going to get 100 pi is less than our cutoff frequency, which is going to be less than our sampling frequency, which was 250 pi minus our maximum frequency, which was 100 pi. So we're going to get that our cutoff frequency for a low-pass filter to recover our signal needs to be between 100 and 150 pi. And that's going to be our answer. Does that make sense?
Sorry, I stepped away for like 5 minutes, so I'm kind of like lost, but not your fault.
All right, I'll give you a quick synopsis. So we're going to take our original function and our impulse train. And when we combine them, we're going to get a graph that looks something like this, right? Where at each interval of our sampling frequency, we're going to have a copy of our original signal. And the bounds of that signal are going to be our sampling frequency minus our plus or minus our maximum frequency of our signal. So we want to find a cutoff frequency for a low-pass filter that's going to include our original signal, but not going to include any sections of copies of our original signal. So we need it to fall in this region here between the upper bound of our signal and the lower bound of the next copy of it. And we just denote that as this upper bound here needs to be less than our cutoff frequency, which then needs to be less than the lower bound of our next copy. Does that make sense?
Got it.
Okay, perfect. Any other questions? Okay, then I will go ahead and pass it off for the last question of the recitation.
Let's go. So we are given a signal x of t which has a Nyquist rate of omega naught by 4, and we are asked to determine the Nyquist rate for another signal which is a function of the given signal x of t. Let's go. So we are given x of t, which has a Nyquist rate of omega naught by 4, and we're given z of t as a function of x of t. And we are asked to find the Nyquist rate of c of t. And to do that, we would firstly find the transformation for it. Z of j omega is equal to 5 times x of j omega convoluted with pi by j delta omega minus omega naught minus delta omega plus omega naught. And now we shall, so convolution of any function with the delta function is just a shift. So we are going to apply that here. We would have z of j omega is equal to 5 times, let's get the pi and j out, and we would have x of j times omega minus omega naught plus x of minus j times omega plus omega naught. And now, okay, I will have to find a new whiteboard. I'm switching in 3, 2, and 1. Okay. So initially we had one signal. Let's say this is our x of j omega. And now this signal became 2 signals with this frequency of omega minus omega naught. And this one is omega plus omega naught. Yep. Yep. So, and this one would be minus omega naught. And the frequency of this entire 2 signal system is omega plus omega naught, because our signal from here, it became a bigger signal with omega plus omega naught as its frequency, the largest frequency. And we will write this as any value of omega that is greater than omega plus omega naught would be equal to 0. And from here, we can find the Nyquist frequency. Our omega is given as omega naught by 8. And we just add it with omega naught to find the Nyquist frequency for z. And this would be 9 omega naught by 8. And to find Nyquist rate, we would just multiply the Nyquist frequency with 2. And this would give us 9 omega naught by 8 into 2. This is 9 omega naught by 4. That's it. Any questions? Okay, that's it for this recitation then.
Thanks for coming, everyone. If you have